Okay, so yesterday at the end we talked about shares inequality, and in particular we prove a special case of that. So we show that if you have three random variables x, y, z, then the entropy of that, twice of that is upper bounded by h of xy plus h of yz plus the entropy of xz. And you can view this as like some sort of like you want to upper bound the entropy of a top, like the entropy of a tuple by part of its tuple and ask like what's the best inequality we can get. And indeed, shares inequality basically answers this in full generality, saying that if you have sets A1 to AN, M sets, that is underground set N. So you should think of I have n random variables x1 to xn. And each set AI would record some part of these random variables. For example, in this case, my ground set is 3. I have 3 random variables. And A1 correspond to these 2 random variables. A2 correspond to these 2. A3 correspond to these 2. And in general, we want to understand like we have n random variables, and given a collection of subsets, what inequality can we get? And the shares inequality says that if these sets A1 through AN covers the whole set k times, at least k times, meaning that each element is appearing in at least k of these sets, then we can prove the following inequality about the entropy. Let me first write down the notation and then explain what they mean. So here, when I write x sub a set, meaning that I'm just looking at the tuple correspond to these indices, which means that this is the tuple xa1 to xan, ar maybe, if A is the set A1 to AR. So indeed, this case correspond to you have n equals 3 and you have 3 sets 1, 2, 2, 3, and 1, 3. Does that make sense? And basically, if you look at the set, I said 1, 2, 2, 3, and 1, 3, each element is appearing in exactly two out of the 3 sets. So it's covering 2 times, at least 2 times. So here I can prove it with k equals 2, meaning that I have k like 2 times the triple of the entropy of the triple is upper bounded by the sum of the entropy of each partial tuples. Okay, so let's see how to prove this.
So equality holds when all xi are independent.
Sorry, okay.
Equality holds when
there are some edge cases, but if they're all independent, equality holds. But if you want the other way around, you like there are some like connectivity conditions like I mean you could. Okay, so you'll see in the proof like when does the equality holds, but I mean if they are independent, the equality definitely holds. Okay, so maybe let's see the proof. So remember we have this inequality about some modularity. We prove when we're talking about the property in the first day. So basically it says that if you look at yes. So Okay, so in the first day, remember we proved something like this. We said we have xyz plus h of z is less than or equal to h of xy plus h of xz. This is the submodulator we proved in the first day, right? And indeed, it implies this one because you could think of this z as their common intersection and x as the extra element, like extra random variables that is inside AI but not in AJ, and y to be the random variables that is in AJ, not in AI. So this z will be exactly this term, and this xyz will be exactly the union, and xz and yz will be these two sets respectively. So we have this inequality. That means we can start from the right-hand side of this inequality and keep doing this submodularity operation, meaning that each time I pick two sets and replace that by their intersection and their union. So I can do the following operation. And by doing this, the right-hand side is decreasing. So I mean the right-hand side of this inequality is going to decrease or like non-increasing. So the entropy of a new one is upper bounded by the entropy of the old one. And note that if you replace these two sets by these two sets, the resulting set family still covers nk times. So yeah, after replacement, still covering nk times. At least k times, I mean. That means we can keep do this operation until we cannot do it anymore and see what's the result. So let's keep doing this. So imagine if you have two sets AI and AJ, that one does not contain the other, then doing this operation will give you two new sets, one being larger, one being smaller, right? And you can prove that this can always be done in finitely many steps. And the hint is that you look at the set size and the set size of a new sequence that will measurize the old one. But you can that's an easy exercise, so let me skip that. And so after doing all these replacement, you get a sequence A1 through your new set family A1 through AN. You can without loss of generality assume that one is contained in the other. Does that make sense? Because if you have two that does not contain the other, you just replace that, and the new one, this one is contained in this one, and you keep doing this. Okay, but in this case, we know since this set family still covers at least k times, so the first k of them, they are all the whole set N, my whole ground set, right? And in particular, the entropy of the sum of my new A1 to AN, or maybe let me call it A1 prime to AN prime, is at least the sum of the first k of them, which is k times the entropy of xn. Right? Because I can throw away all the remaining sets and only look at the first k of them. And each of them give you an entropy of xn, x1 like the whole tuple. So that tells you this, that gives you this inequality exactly. And since along the way we are decreasing our entropy, so this one is upper bounded by the original right-hand side here. So far, so good? Okay. So I'm going to tell you several applications of shears inequality, and maybe let me start with the most basic one, which is the Loomis-Whitney inequality. That tells you about the volume of some sets versus its projections. And it is indeed related to some sort of Holder's inequality. So here I'm going to write it as so it's Loomis-Whitney, but it's sort of a special case of generalized Holder. So let's say you have a set S that is in the. So here I'm instead of working with R, I'm working with some think about grids and working with Z instead. So let's say we have a set in Z to the N. And let's assume this set is finite. For our like just for simplicity, if it's infinite, you can also have a similar argument. And also assume we have sets A1 through AM that are inside N. And these sets A1 through AM will be correspond to the direction we are going to project. So I guess let me first tell you a simpler version. So the kind of the motivation is that if you have some body inside three-dimensional space, I want to understand the volume of this one versus the volume of all of its three projections onto the xy plane. So this is the x, I guess this one is the x. Okay, I'm drawing y, z. So this is the xy plane, and also onto the x. This is yz plane, and you can see another projection onto the xz plane. You want to understand the volume of the relation between the volume of this guy versus these three volume of projections. And in general, I want to understand if I have a body or like any set in n-dimensional space, I want to look at its projection onto the coordinates A1 and coordinates A2 and so on. Look at the relation between the volume of the original body versus the volume of the projections.
A1 to M not necessarily cover N.
I'm going to say that. So it will have the same condition here.
Okay.
Yes. So in this case, you can see this x, y, y, z, and xz covers n 2 times. So there will be a like k equals 2 and some like this parameter will be involved. Okay, so I'm still going to assume this covers at least k times. Then we can define a projection. Let's call it P of AI. It's a projection map from Z to the N to Z to the AI. So basically, I'm just dropping all the coordinates that is irrelevant to AI and only look at the coordinates on AI. So this is a projection map. Then we have the following inequality. So here by absolute value, I mean the projection, the size of projection, and since I'm working with Z to the N, it's just a counting measure. So basically it says that if you are in three-dimensional space, the volume of this one, if you discretize that, but okay, I'm kind of identify the counting measure here and the volume measure here. You can easily prove that by compact argument, but if you look at the volume here, the volume square will be upper bounded by the volume of these three projections. And the square basically comes from the fact that x, y, y, z, and xz covers the coordinates twice. Okay, is the statement clear? So let's try to prove this using shears inequality. And as you can see, we have the same condition on the set, like the coordinates we are projecting, and these you can think of this as like I'm starting from an n-dimensional thing and projecting to these AI coordinates. So basically, I want to try to apply shears inequality in the same fashion. And remember yesterday, or like in all the application of entropy, where we always started with sampling the things on the left hand side, on the side that we want to upper bound it. So I'm going to sample something uniformly random from S, and that will give me a point because S lives in the n-dimensional space. So let's sample x1 to xn. So let's sample x1 to xn uniformly at random. Then basically the log of the size of S, since we are sampling uniformly at random, this will be the entropy of x1 to xn. And in our notation, this is entropy of x sub bracket n. And so we know all the index set here satisfy the same condition as shares inequality, so maybe we could just naively apply shares inequality and see what will happen. And in order to apply shares inequality, I want to multiply by k in front so that I can apply this inequality here. So shares inequality tells us that this is upper bounded by the sum from I equals 1 to m, the entropy of x ai. And indeed, the left-hand side is exactly s to the k, right? So this is indeed the left-hand side here. So we only need to show that the right-hand side, this one, is upper bounded by the log of this one. But you know, this is indeed true, like term by term, because you know this entropy x sub ai is supported on the projection, right? So if you look at the support, this is inside the projection of my set S, because I'm throwing away all the irrelevant coordinates and only the coordinates in AI remains. So that would be exactly the projection. So this is supported in the projection of S. That means this one, the H entropy term is upper bounded by the log of the size of the projection. And if you take the exponential back, it gets to exactly this inequality here. Okay, so that's how you prove Loomis-Whitney inequality, and indeed you can pass by compact argument, replacing all the z by r, and replace the absolute value by the volume or the measure of the sets. Okay, so here I wrote Loomis-Whitney and generalized holder. So you might wonder, is that related to holder? And indeed we can prove a form that is indeed generalizing the holder's inequality. So again, we start with sets A1 to AN, sorry, A1 to AN that lies inside N and covers N k times. So this is always our assumption. And now I have functions supported in, say, z to the n. So let's say, but I have functions supported on each of the set, like each of the projections set. So this is z to the ai, and they are non-negative. And I guess the case you should think of is that in the usual holder, you have this ai, sum ai squared times sum bi squared is at least sum of ai bi squared, right? So you should think of this as these ai are supported on the x-axis. So you have a function on the x-axis, and these bi you have a function on the y-axis. And so each value here will correspond to the tensor of this function versus this function. That will be the ai bi. And in this picture, in this term, I'm going to do like the generalization of that, saying that. Why did I change notations? Okay, let me change it back. Saying that if you have a projection map defined as before, then indeed the sum of first finish that. I pose in my note, but it's fine. I from 1 to n, and you look at any point in the n-dimensional space, you project onto the subspaces, and then you evaluate at that function correspond to that subspace and take the product of them. This is upper bounded by you first take the product, and then inside you take the sum. Z to the AI fi of y to the k's power the 1 over k. So in this case, like for this inequality, you should think of like I'm just taking several points here, taking all the points in the two-dimensional space and look at its projections. So for this point, you get the value ai, and for this projection, you get the value bi. So you project and evaluate the function. So the sequence ai is kind of a function of the index I. And so this point you get ai bi, and for this point you get another ai bi, and you sum them up. That'll give you a right hand side. And I guess I'm moving this one to the left hand side. So that would be the left hand side here. So this term will be this term here. And on the other side, I'm just collecting all the points on the x-axis and sum ai squared. So I'm collect all like product over all the x's, and for each axis, I'm doing this evaluate the function raised to a k's power, and then product multiply them, like summing them, and then multiply them and take the 1 over k's roots. So basically, this generalizes the Cauchy-Schwarz inequality, and it also generalizes many forms of Holder's inequality. So I will call it generalized Holder. Okay, so maybe let's see how to prove this using the Schwarz inequality. And I would like to remark, if you just pick fi to be a function, the indicator function of the projection, then that will give you the equality right there, the Loomis-Queeny inequality. So for this one, I guess we also want to sample random variables that correspond to the left-hand side. But in order to do that, let's do a special case. And it is sufficient to show this inequality for fi that has integer values. And once you show this for fi being integral functions, you can do like dividing by the common denominator to pass to rational functions, like not rational function with rational values, and do compact argument to pass it to real value functions. Okay, so it's sufficient to do this. And in this way, like in this setting, it's much easier to sample something that has entropy equals to the log of left-hand side. So I'm going to sample n plus m many random variables. And these n random variables are kind of in the same role as these x1 through xn here in the previous proof. And these y1 through yn will kind of tell you what the function fi, the value of fi is. So I'm going to sample this so that 0 is less than or equal to the value yi less than or equal to f of the projection of x1 to xn. And I'm going to sample this tuple uniformly at random. Is that clear? Like the way we define this random variable. So basically, you could think of this like the sampling probably you won't. So yeah, you could think of this sampling process as look at all the possible spaces, possible tuples that satisfy this condition here, and pick uniformly one out of them. Although this inequality is involved x1 to xn on both sides, on the right hand side. And this indeed counts the left hand side here. So the entropy of x1 through xn and y1 through yn is indeed the log of the left hand side. Because once you fix each x1 to xn, you get a point lowercase x. And for that lowercase x, you have fi, like this fi function, many choices for yi, so you just take the product of them. So that will be exactly this product inside here. So the number of tuple exactly counts the left-hand side. So you sample something uniformly random, you get exactly the log of the left-hand side. Yes?
Why the function f is the image is the real.
Yes, so here I'm assuming I'm showing that for integer value functions. And you can pass to real by dividing by denominator and compact argument. And here I'm also kind of cheating by assuming that all the function fi have finite support, but you could prove infinite support in the same way, like using compact argument. Yes, so here I'm assuming integer z, so I'm sampling all the yi to be integers between 0 and this number. Maybe I need less than. So that the total number of outcome is exactly fi. Okay, so once we sample this tuple, our task is to try to split all the things related to AI. Like here we have a product form, so we want to upper bound the entropy of this by something related to AI in X. So I want to have something about XAI, because that corresponds to the points inside Z to the AI. And I want to also split YI out, because this yi corresponds to the function, this function here, which is appearing here as well. So I want to split using shares inequality to split this whole tuple into something about xai and yi. So the first thing I'm going to do is to apply the chain rule to first split x versus y, these capital X and capital Y's. So if you look at k times the log of left-hand side, or like k times the entropy of x1 to xn, and y1 through ym. This is the same as you apply chain rule, so you get x1 through xn, and k times the entropy of y1 through ym, given x1 through xn. Right, this is chain rule. And the next step, I'm going to upper bound this as usual. I'm just applying shares inequality in the same way as I did there. So this gives me sum over I, the entropy of xai. And I'm going to upper bound this term by doing drop conditioning. I'm going to just drop all the coordinate that is irrelevant to AI. I'm going to first do the subadditivity to split all the yi, becomes y1 to like y1 condition all these things and y2 condition all these things. So this is the same as sum over I, the entropy of yi, condition x1 through xn. This is subadditivity. But I can further upper bound it by dropping all the irrelevant conditions. So for yi, the kind of relevant one are those having coordinate in AI. So I'm dropping the others. So this is upper bounded by entropy of xai. Plus this part, I'm going to just drop it to y condition xai. And here I have a k here. I have sorry, I mean it's a k here. So this k is this k is this k. Right? So now we kind of split everything for each different AI. For each I, we split all the things related to I out. So I want to prove this, the log of this term is term by term upper bounded by the entropy of these. Okay, so if you know if k is 1, I can simply just combine these two terms and get the entropy of yi given x, the entropy of a tuple xai and yi, right? If k equals 1. But if k equals 2, it's kind of like the situation we had yesterday. We have an edge x and y. And if I can resample another vertex z, sorry, yesterday we did it another way around. I kind of have this, the entropy of this is y, and the entropy of this is indeed x given y, right? If I first sample this one and then sample x given y. And if I have two copies of x given y, I can get exactly by resampling this x, condition on y, so I get another copy that has the same entropy that is x given y. So here I'm going to do the same thing. I'm going to just condition on xai and resample yi k times. So now I get k conditional independent random variables yi1 to yik. Right? So I'm just resampling this yik times given xai. And once you do this, we can write this entropy as the sum of the entropy of.
Is there something wrong with this subscript I? Because I think for x, the I varies from 1 through n, and for y, the I varies from 1 through n.
Yes. So AI is a subset of n.
So my question is whether there should be j.
No.
No, it's the same I.
Yes,
Same I.
So I fix the I and I get a set AI that is the index. I guess you could think of the limit like the 3-dimensional case. So A1 would be the coordinate 1, 2, and Y1 correspond to this set.
So for the last summation is that so there should be a bracket, right? Like the h of xai plus k times h of yi addition.
This one?
The last one.
This one?
The next one.
This one?
This one. Yeah. So the underlying part is actually a bracket, right?
But like which one?
So the sum is taken. The sum is taken for the addition for the h plus.
Yeah, so this is sum from I equals 1 to m.
Yes.
And is that your question?
So my question is the summation from the previous line.
Yes, this
The next summation. This one. Sorry, the k times sum of I. Yeah, this one. So what happens to this summation from this line to the next line?
this one to this one?
Yeah.
I mean, in our notation, you can write this as x bracket n.
Yes.
And I'm just dropping all the things that is not inside AI. So this is drop condition.
I see.
Okay, so we sample these and we know these are conditional independent. So this, if I compute the entropy of xai and yi1 to yik, this is indeed the left-hand side. Because I mean, you can do the side calculation and use the conditional independence. So if you want to compute the entropy of this one, you can use chain rule to first split this term out and then condition these terms. And I mean, and then sequentially get these terms. So it's the same as xai plus h of xi, sorry, yi1 given xai plus h of yi2 given yi1 and xai, and so on. Right? This is just chain rule. And here you can use the conditional independence to cross out this term. And in the next one, you can also cross out all the y's. And you know these, like this term and this term all have the same marginal distribution as yi given xai. So this term is exactly one of this term, and this term is another copy of this term. And you have k of them. So this entropy is indeed this entropy here. I want to make sure everyone are okay with this conditional independent and compute the entropy step. And we will use this idea much more later on. Is that okay? Okay, so we got an entropy of this tuple. So it remains to show that this tuple is supported on something of the size, this one, right? And indeed, you have this xai is supported on z to the ai. And for each yi, it lies inside the value from 0 to this number. And you have k copies of yi. So you have k of them. So you raise to the k's power. So I'm just saying, if you look at the support, the size of the support is indeed upper bounded by the sum of y inside z to the ai times fi of y to the k's power. Because you fix any x, you fix any outcome of these x sub ai, I call it this lowercase y. And for these capital y's, each of them is supported on 0 to this number minus 1. You have k of them, so you have like this number to a k's power many possible outcomes for these yi. Once you are given the outcome of this capital X. So the support size is indeed upper bounded by this. So you can use uniform bound to get the right-hand side, and that will give you this inequality here.
This it shares inequality. Is there any condition on the random variables x, y, right? Are they just any arbitrary?
And any arbitrary random variables, they can be correlated, they can be any random variable. In all these proofs, you just need them to have finite supports and discrete. Okay, so maybe let's move back to the world about graph counting or graph homomorphisms. So the next topic about application of shears I would like to talk about is the number of independent sets. And the motivation question is quite simple. Suppose that I give you a graph G. I want to ask which edge maximizes the following quantity. So let me write this. Okay, let me first cross out this. So the motivation is like which edge maximizes the following quantity I of h to the 1 over v of h. And I'll explain why this normalization occurs later. But I want to ask which edge maximizes among all the irregular graphs
What is IH?
Oh, sorry. IH is the independence number of H. Sorry, the number of independent set of H. And so is the question clear? And I think that this is indeed a homomorphism problem. So this is it. And indeed, the number of independent set inside the graph H is the same as the number of homomorphisms from the graph H to the following graph with a self loop. This is because if you have an independent set here, I can just simply map the independent set to this vertex and map all the other vertex in H to the other vertex here. And that's a bijection between the number of homomorphisms versus the number of independent sets. So you can ask a more general question, asking that now I have this fixed G, which H, again, among all the D-regular graphs, I can ask which H maximizes the hom from H to G, normalized by 1 over V of H. And I guess now the normalization is kind of clear because for each vertex in H, if there's no restriction, you have a way to map into G. So you could think of like each edge has some fixed number of choices, and this normalization is just saying that if you have VH many vertices, each of them has like some amount of choices. Then I want to ask what on average the number of choices each vertex has. So I'm doing this normalization by taking the 1 over VH root. Okay, and turns out this problem was solved. I mean, the first problem was solved, and I will talk about the result a little bit later. But using entropy, one can prove that among all the bipartite edge, the maximizer is always the KDD, the complete bipartite on D vertices.
I have a question. What is constant related to that?
If you don't have like degree constraints, then I guess the trivial maximizer is just one vertex because you have no restriction. And I think when D is smaller, you get like the quantity will be larger. So you want to put some degree constraints on the graph H. Okay, so there is a theorem by for the independence number and by Gilman and Tetali. Saying that if H has n vertices and irregular and bipartite, then the number of hom from H to G normalized by the number of vertices is upper bounded by the same quantity with KDD in place of H. So here the number of vertices in KDD is 2D, so I'm putting 2D here. Okay, and indeed the proof is quite similar to what we did in generalized holder. So as usual, we want to start with sampling something on the left-hand side. So let's sample x1 to xn. So okay, let's assume Let's assume this is our graph H. Let me do it larger. Yes.
We replace the condition irregular with the mean degree D, you still have this theorem.
Okay, I will state the general like degree sequence version of this later, but yeah, you'll see that after I prove this. So let's say you have this graph H, that is a bipartite, you have some edges in between. And this is V1 to Vk. And this is U1 to UK. So I want to pick a homomorphism F from the hom of from H to G uniformly at random. And I'm going to identify this homomorphism as the outcome of each vertices. So I'm going to call Xi the outcome of F of EI, and Yi the outcome of UI. So Xi and Yi are random variable, like random vertices in G as usual, like it's always the same, similar to what we did for Sidorenko. So Xi and Yi are vertices in G, and Xi correspond to the vertices in the left-hand side, Yi correspond to the vertices in the right-hand side, and the collection of all the Xi and Yi as a tuple give you a copy of hom of H inside G. Okay, so as usual, we have the entropy of Xi to X1 to Xk. Oh, one thing I forgot to mention, since it's deregular, so the number of vertices on both sides are the same, so I'm assuming it's the number k. So I have X1 to Xk and Y1 to Yk is the entropy. Sorry, the entropy is the log of the hom from H to G. Okay. So now I want to take some sets. I want to apply shears inequality. So I want to take some sets that covers this K several times. Okay, sorry, but for the inconsistent notations, but I want to take AI to be J, that is, so that Vj is inside the neighbor of UI. So basically, I'm just, for each UI here, I'm looking at its D neighbors and look at the corresponding random variable x1, x sub something, and collect them to be my AI. And I'm going to apply shears on the X side and do some similar trick as what we did for generalized holder on the U side or on the Y side. So we know this covers.
But did I miss anything? Why is the number of vertices the same from both parts?
Because it's deregular and you do the double counting on number of edges. Yes. Okay. So we know this covers R, since there are variables in the X side. Let's see, covers. So I know 13. Covers K. Covers K at exactly D times. Yes. Because you know that for each vertex here, it's deregular, so it's inside the neighbor set of D sets here. So this collection A1 through AK covers K D times. Okay, so we know by shears inequality, or let me first decompose X1 to Xk and Y1 to Yk in a similar way as before. This is the same as D or times the entropy of X1 to Xk, and plus the conditional entropy H of y1 through yk given x1 through xk. And I'm going to apply shears to this part. So by shears inequality, this is the same as h of xai. This is upper bounded by h of the sum of h of xai. And for the second term, I'm going to just throw away all the info. I'm just going to do the same thing as what I did here. I'm going to first use subadditivity to split all the terms and throw away irrelevant information. So this is upper bounded by d times h of yi given xai. So the idea is the same here. I just do this step. I first do subadditivity to decompose, to split all the yi, split y1 through yk, and then throw away irrelevant information so that it only remains xai. Okay, so I can kind of combine these two summations. So this is a whole summation. And in the picture you should have is that for each I, this is yi. And xai are the neighbors of yi. You have d of them. So you have d neighbors. So this is xai. And now you have d copies of yi. So again, I can do the same trick. Resample this yi d times. So I get yi1 to yid. And this entropy is the same as the sum of xai and yi1 to yid. So this step is also the same as the step in the generalized folder, but we're just playing with graph instead of playing with those projections. But all the entropy calculations are the same. Okay, but in this case, since we're resampling yi to get these yi1 to yid, we know that all the edges must be connected. So this should be a complete bipartite. E vertices here and D vertices here. So this, and we know this is a complete bipartite that's supported inside G. So it's a homomorphism copy of this complete bipartite KDD inside G. So this is upper bounded by the sum of log 2 of the hom of KDD in G. Okay, and how many copies do we have? We have k copies. Remember, this I sums from 1 to k. So here you have k copies of that. That means we show that the hom from H to G. Okay, let me finish it here. Is upper bounded by k, this number raised to the k's power. But you know, if I multiply this k, this n to the right hand side, n over 2d should be exactly k. You can do this double counting down here. So in between you have k times d many edges. And what is n is the number of vertices, so n is 2k here. And you can do the double counting, and so k over d is indeed. Let's see. Okay, whatever. You can do double counting. So that will give you exactly that inequality there.
Left hand side we have power t. Homomorphism HG power t is that and bonus. Homomorphism of KD is the power.
Sorry? Which?
I mean left hand side should be a power of t because you times t and by shares that.
Ah, right. I forgot this d. That's fine. So thank you. So here I have a d missing. That's why I didn't do the double counting correctly. So if you divide this, like if you divide it by d times k, or like take a 1 over kd's roots, you get 1 over k here, 1 over d here, and like what you know, n is 2k. So you encounter that inequality. Okay, so let me tell you some like progress after this theorem being proved. So first, about the counting independent set problem, is completely solved by Yufei using a clever trick called bipartite swapping trick. So after you prove the bipartite version, if you have a graph that is not bipartite, you can do some swapping and show that the number of independent set will just increase. And once you do this swapping, you swap into a bipartite graph. Okay, you need to first take a double cover of that graph and do the bipartite swapping trick. And once you get the bipartite graph, you just apply the result by Kahn and Gauvain-Teplani, so that you can prove the maximizer. If like the maximizer of the first problem is indeed KDD. So if H is deregular, then I of H, 1 over n, is always upper bounded by I of KDD to the 1 over 2D. And later, Ashwin Matab and Cynthia and Yufei, it's Shani, Stoner, and Zhao. They show that if H is deregular and triangle free, then this inequality holds for any target graph G. And indeed, they have a more general upper bound, which they call the reverse Sidorenko inequality, saying that if I just, okay, there's something wrong on my note. So if I just assume H is triangle free, not necessarily deregular, I have a similar upper bound in terms of a degree sequence of H. And indeed, they prove that the Hom from H to G is upper bounded by, you product over all the edges inside H. You compute the Hom of the corresponding K complete bipartite graph. So the Hom of K du dv, where du dv are the degrees of U and V inside the graph G. So inside the graph H. So I look at the Hom of this into G, normalized by 1 over du dv. Then the number of Hom from H to G is always upper bounded by this quantity. And you can check that if H is deregular, then all the du dv are d. And this becomes 1 over d squared, and you take the product, you compute the exponents, that will give you exactly the inequality by Gauvain and Teplani. But here they only need to assume that H is triangle free instead of assuming bipartite. And in the same paper, they also prove the version for if you drop the triangle freeness, in general, this inequality is not true. But when the target graph G is a clique, then this is true. So H is again triangle free. So H don't need to be triangle free anymore. And this holds this inequality holds when G is a complete graph called KQ with possibly some loops. With parallel self loops. So for example, this graph, when you are counting the independence number, this graph is just K2 with one loop. And indeed, they generalize this. And in particular, if the graph has no loop, you are just counting the number of Q colors inside H. So it's kind of like the Q coloring, but you are allowed to have some loop. Okay, and there are also several conjectures that are really hard. So one conjecture is that in the same paper, they conjecture that as far as G is antiferromagnetic,
For the for the last one, should that be reverse inequality or
this one?
the KQ with L groups?
This one? No, it's still upper bounded by
It's still the same thing.
yes.
In the exponent, is that du plus du
du
or
times dv.
times du?
So that is only for arbitrary H, but with G to be that specific graph.
Yes, yes, yes. Okay, so for G fit in this one. Yes, and they conjecture that if G is antiferromagnetic, meaning that the adjacency matrix has only one positive eigenvalues. Has only one positive eigenvalue counting with multiplicity, then this also holds. So far, so good. Okay, so in the next part, I would like to talk about probably the one of the most famous case where the shear inequality was applied, and I believe this is the first one where it is applied in the full generality. It's a paper by Shears, Shaw, Graham, and Frankel. It's about the triangle intersecting family. So let me start with what is an intersecting family. I guess many of you know this better than I do. But let's say F is a family. That is, okay, let me just write in notations. So F is a family supported on n elements such that the size of A intersecting B is always at least 1 for any two sets A and B. That is in F. Then we call F intersecting. And I guess one of the most easy way to ask extremal combinatorial problem is that asking what's the maximum or the minimum possible F. And in this case, we're asking the maximum possible collection or number of sets that we can get that are intersecting. And for this one, it's easy, right? So, if I take A and A complement, only one of them can be in my collection F. So the fraction is at most 1/2. On the other hand, you can take the star construction or like a construction that is more than a half of elements, more than n over too many elements. These all give you a construction reaches that upper bound I said. So the max, this is easy. And the answer is 2 to the n minus 1. Okay, so what about I give you a family of graphs. So I have many, many graphs. And I want to ask whether I want to have a property that if you take any two graphs, they are intersecting in at least one triangle. So let's say F is a family of graphs. On the vertex set, N. Again, we are fixing the number of vertices, but you should think of these graphs as the edge sets. And I want to have a property that A intersecting B contains at least a triangle. For any two graphs, so here A and B are graphs. And for any two graphs, they intersect in at least one triangle. They could intersect in more edges, but you should at least find one triangle for me. Then what is the maximum fraction or like maximum number of set of graphs I can get? So there's a nice theorem proved by from Graham-Frankel and Shears, saying that the fraction is at most 1/4, and indeed you can take a following easy construction, get 1/8. So if you just fix the polar graphs containing the edges, that already forms a triangle. So that's kind of similar to the star construction. I fix the minimal witness so that every set is intersecting in this witness. Then in this construction, I get 1/8 out of all the possible graphs. And remember, the number of possible graphs is like 2 to n choose 2, because you have n choose too many edges, and for each edge you can pick or not pick them. And as I mentioned, the upper bound. This is a theorem by Chao, Graham-Frankel, and Shears. Oh, it's important. Saying that the size of f is always upper bounded by 1/4 of all the possible graphs. And indeed, there's a later theorem, not using entropy, but using like spectral theory, like analyzing the spectrum of like all these things. They get that this is indeed a type 1. Okay, so today I'm going to show you how to prove this one using Shear's inequality. Okay, so I'm going to just show you the proof when n is even. And for n is odd, you can prove it quite similarly, but the calculation will be slightly more annoying. You'll see why. So I'm going to just show you the proof when n is even. And if I take the graph H, so graph H is also supported on the ground set of vertices n, 1 through n. If I take H to be the disjoint union of two complete graphs, Ks and Kt. So in the picture, you should think of like I have an H that consists of, this is S, this is a complete graph, and this is T, another complete graph. And you know that if I take any graph here inside my family, any two graphs, they're intersecting in a triangle, right? And that triangle, if you put it on this graph, it gives you at least one edge here or here. Okay, so at least like this set S and T, the graph H will indeed capture one of the edge. So I'm going to do kind of projecting onto these all the possible graph H, possible by partition into S and T. I'm going to project that, and after projecting, I know my set family, any two of them are intersecting in one edge. And I'm going to apply the easy intersecting bound, fraction 1/2, after doing projections. So let me tell you how to execute this idea. So S and T are disjoint union to n, like it's a partition of n. Then we know that A intersect B intersect H has size at least 1. So by size, I mean the number of edges remains for any A and B. Okay, so let's try to see how many possible projections can we do. So let me call H1 to HR, all possible H's. And okay, and here I'm doing a balanced partition. That's why I need N to be even. So in this case, we know R. We write it here. So R is N over N choose, N choose N over 2 divided by 2, right? Because you have N vertices, I can pick N of them to be my set S. So I have N choose N over 2 many ways to pick S. But having this graph ST is the same as TS, so you divide it by this 2. That's the total number of H we can project it to. Okay. And we want to apply the Loomis-Whitney. I guess in this case, it's slightly easier to apply Loomis-Whitney than using shears. So I'm going to tell you what you get after applying Loomis-Whitney's inequality. So I'm going to apply this to the projection onto H1 to HR. And I know that H1 to HR covers each edge. So you should think of each edge as one element in the shears or Loomis-Whitney inequality. And each edge is covered by the same amount of times, right? Because of symmetry. So let's assume each edge. So maybe we can explicitly compute the number. So we know it is covered by k times, and this k is given by, we put the number here, by n minus 2 choose n over 2. Because what you want to compute how many edge that contains this edge inside either S or T. So basically you are just asking like how many ways can I pick the other n minus 2 elements that are in the same blob as these two vertices. So the number of times that this edge is covered is n minus 2 choose. I guess this n over 2 minus 2 is what I said, but you can think of like choosing the other side. So this is the same as n minus 2 choose n over 2. Okay. So by generalized holder or by Loomis-Whitney inequality, you get this f to the k is less than or equal to the projection. So the projection of f onto the set hi. And what is f what is f restricted to hi? This is indeed a set where you take A intersecting hi. Right? Because by projection, I mean that I don't care about all the other information. I only care about the information on these in this edge. So I'm just intersecting with the hi with each hi. Okay. But we know this is an intersecting family. So what is the size of that? The size of that is upper bounded by 1/2 of all the number of edges inside hi. So this is upper bounded by the number of edges in hi. Hi. Okay, let me put this as -1 here. And we know this is the same as 2 to the number will be n 2 times n over 2 choose 2, because the number of edges here is n over 2 choose 2 and n over 2 choose 2 here, and -1. Okay, so you just plug this in, you get f to the k is less than or equal to 2 to the 2 times n over 2 choose 2 minus 1. This is this. And you raise to the rth power because you bound each term by this number. So this is raised to the rth power. And if you divide this to here, you get r over k. Okay. So you compute the ratio between r and k, get that r over k is indeed n minus 1 over n over 2 minus 1. So you can indeed compute this binomial coefficient and just ask you to trust me. So this is the same as, okay, so let me just replace this by n minus 1 over n over 2 minus 1. And, okay, let me skip the calculation, but you'll get this is n choose 2 minus 2. Okay, upper bounded by that. It's just playing with the binomial coefficient slightly more carefully, and you'll get this upper bound. So that recovers the 1/4 upper bound. So far, so good.
Second equality should also be an equality. The second equality.
This one,
The second equality. The second one.
second,
The first one.
the second
Yeah,
equality.
yeah.
Ah, thank you. This should be equality. Or the other way. Thank you. Yeah. So for that one, I'm applying the easy problem here. Okay, so we have 10 minutes left. Let me tell you something light, something easy. And this will be one of my favorite problems. And so the question is quite simple. People are going to count the number of triangles in the graph. And you know, if I fix you a number of vertices, I know the number of triangle, the most number of triangle I can get is just take a complete graph, and that problem is boring. So it leads us to the Kruskal-Katona type problem. So instead of fixing the number of vertices, I want to ask you what's the maximum amount of triangles if I tell you the number of edges instead. So here you are allowed to use unlimited many vertices. But you are only allowed to use m edges. You want to ask, what is the most amount of triangle you can get? And you might think about this like, if I just try to squeeze all the edges together to try to make it as tight as possible so that I get a click, then that might maximize the number of triangles. And indeed, this is a truth, and it was proven independently by Kruskal and Katona. They show the following theorem, saying that if the number of, okay, I'm going to state it in this way. If the number of triangles is A choose 3 plus B choose 2.
Wait, but by the way, for the previous one, so that's the proof. This proof shows something slightly stronger than the 1/4, because
Yeah, I think if you run all this calculation, you get you get some lower order term about n involved. So that's like 2 to the negative 2 minus something about 1/n or something.
So does this have any kind of motivation to the 1/8 proof, or
No.
that's completely different?
I think that's completely different. So for the 1/8 proof, they analyze the spectrum of the stack. Yeah, sorry, I forgot the detail, but
So it's not just like
they do like spectral method and really
so
have a careful analyzation of these like eigenvalues. I think someone knows this better than I do.
Yeah, I think there are some similar idea. Like they analyze this two click construction into like we add some operator capture the structure like the complement of this two click and acting this operator to the the set family and compute all the eigenvalue
Right.
and using the a generalized Hoffman to show that.
I see. Yes. Any other question? Okay, so let me keep giving you the brief overview of the theorem by Kruskal-Katona. And indeed, they prove this independently, so it's two different papers. So let's say the number of triangles are of the form A choose 3 plus B choose 2 with A at least B, A greater than B and B is at least 2. And you know any number can be expressed in this way. Then the number of edges need to be at least A choose 2 plus B choose 1. So the optimal graph is that you take a click. And if you have spare edges, you just try to connect the edges to some of the vertices. And that will give you the most amount of triangle. But you might think of like this form is hard to apply if I want to really use this for some, like if I know the number of triangles, I want to know how many edges, but like this form is kind of hard to apply. Like the first step, you need to rewrite the number of triangles in terms of A choose 3 plus B choose 2, and that already been hard to analyze. So Lobas proposed actually he gave this in one of his books as an exercise, giving an easier version of this theorem, saying that if the number of triangles is x choose 3 with some real number x at least 3, then the number of edges is at least x choose 2. And I claim that it's quite easy to just use shears inequality to prove the following even weaker bound. So it might take you a while to think about like, is this bound weaker than this one? But you could prove that this is indeed a weaker bound. And this is quite easy to prove by shears. So let me just show you a nice simple proof. So again, in this problem, you should view it as like I have a fixed amount of triangles. I want to upper bound it by the number of edges. So I'm going to sample a triangle uniformly at random and try to connect that with some random variables about edges. So let x1 to x3 be a triangle G uniformly at random. So what is the entropy of x1, x2, x3? And someone tell me what's the entropy of x1, x2, x3? Yes. So you need this 3 factorial because here by number of triangles, I mean the number of unordered triangle, but here x1, x2, x3 are ordered pairs. So for each triangle, there are 6 ways to order that. So this is 6 times the number of triangles. And I want to apply shears. Remember, like x1, x2 is always an edge, x2, x3 is always an edge, and x1, x3 is always an edge as well. So I want to apply shears to upper bound by the entropy of x1, x2, x2, x3, and x1, x3. So I multiply by 2 here, and upper bounded by shears. And you know that since I'm picking this uniform at random, all the 3 distributions are symmetric. So H1, H2, the marginal distribution of H1, H2, sorry, X1, X2 is the same as the marginal distribution of X2, X3, and the same as this one. So they all have the same entropy. So for our convenience, I'm just going to write this as 3 times h of x1, x2. Okay, well, we know this is the number of edges. So we know this is supported on edges, so we can upper bound it by the number of edges. So this is upper bounded by 3 log. What should I put inside?
3 times.
So again, we have this order issue. The number of edges is n, but for each edge, there are 2 orientations. That will be both in the support. So this is 2n. Okay, so you connect this upper bounded. So this part is upper bounded by this. So if this is x cubed over 3 factorial, then this is log x cubed. So this is 6 log x. So 3 times of this is larger than 6 log x. So this is larger than 2 log x, which is log x squared. So the number of edges is at least x squared over 2. Okay. Give me 3 more minutes. Let me do the same thing for C5. So indeed, this idea can be generalized to count like any other graphs. So you can also show that if the number of edges in G is n, then the number of homomorphisms of C5 into G is upper bounded by n to the 512. And I guess you might have seen this exponent when I was talking about the number of induced C5s. And this proof is basically the same. I want to sample x1 to x5 uniformly at random. And I want to apply shears. So first I know that the log of the homomorphism of C5 in G is the same as the entropy of x1 to x5. And I know 5 times of that. Sorry, I know 2 times of that. I'm going to multiply by 2. And in the next lecture, I will tell you why I picked this number of 2 and see a more general way of proving these inequalities. But if you apply shears inequality with the set 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1, then these 5 sets are covering all the elements at least 2 times. Actually, exactly 2 times. So this is the number 2. This is h of x1, 2 plus h of x2, 3, all the way to h of x, 5, 1. And you know they are all identically distributed since there are symmetry, or like you can just upper bound each term by the number of edges. So this is upper bounded by 5 log of 2n. And as you can see, I have a 2 here, divided here, give me 5 over 2. So the exponent should be 5 over 2.
So the first line of the proof should be homomorphic C5. I mean, the first line of the two. If you define S1 to S5.
Right. Okay, so I'm hiding this, but yeah, I'm counting the number of homomorphisms, and if you want to indeed count the number of copies, there might be some lower order term issue, and you just need to subtract by those like non-injective maps. Okay, so that's how you prove the exponent for C5, and in next time we'll see like for arbitrary graphs or hypergraphs, what is the correct exponent here? Okay, so that's it for today.